In this video we're going to look at the concept of the radius or a size of an atom. So in order to discuss this, we'll have to first look at expectation values and how we calculate them in spherical polar coordinates. So in Cartesian, that's in 3 dimensions, x, y, and z, by these Cartesian axes here in white. We would calculate our expectation value just by integrating in each dimension from minus infinity to infinity in x, y, and z. The psi star of x, y, and z times the operator a acting on psi, and again taking that whole integral. And in spherical polar coordinates it works slightly differently, and that's because our volume element which we're integrating isn't exactly the same. In Cartesian, the volume element you're integrating, the infinitesimally small cube, its volume is just dx, dy, dz, just the multiplication of the lengths of each of these Cartesian dimensions. Whereas in spherical polar, because of the way we integrate and what these limits of integration are, we have different lengths for what the sides of this infinitesimally small cube would be. That's our volume element for integrating. It would have sides of r d phi, r sine theta d theta, and dr, thus giving us a volume element of r squared dr sine theta d theta d phi. So we're integrating from 0 to infinity in r. We're integrating from 0 to pi in theta, the polar angle. We're integrating from 0 to 2 pi in phi, the azimuthal angle, the projection on the xy plane. And again, just the operator acting on the wave function times the complex conjugate. Okay, so what we're going to look at is the expectation value for radius in the 1s orbital. So this would just be integral from 0 to infinity r squared dr. Let me write r squared dr. Integral from 0 to pi of sine theta d theta, and integral from 0 to 2 pi of d phi. Psi star, the 1s orbital is psi 100. The operator for r is just multiplying by r times psi of 100. Okay, so then our psi 100 is actually real, so it's just equal to our psi star 100. So our psi star psi is just going to be psi squared. And this is equal to 1 over the square root of pi times z over the Bohr radius to the 3/2, z being the number of protons in the nucleus, which is 1 for hydrogen, and then e to the minus zr over a naught. That quantity is also often referred to as minus rho there. Okay, so we can substitute this in. And we notice in here that there's no dependence on theta or phi for this 1s orbital. There would be theta or phi dependence if we went to a p or a d orbital, but for s orbitals they are spherically symmetric, so there's no radial dependence. So we can say that our 1s expectation value, well, we're going to square this, so some things that we can already start pulling out. We can pull out a 1 over pi, because our r operator commutes with multiplication is an operation that commutes, so we can just say r times psi star psi. And psi star psi is just psi squared in this case, since psi is real. So squaring this, we get 1 over pi. Z is going to be 1, so I get times 1 over a naught cubed. Then I do my integrals. Let's do this integral here first, the 0 to pi sine theta d theta, integral 0 to 2 pi, go back and write that as 2 pi, of d phi, then the integral from 0 to infinity, and we have an r squared from here, we have an r from here, so that's going to give us an r cubed. And this psi squared is going to go from e to the minus zr over a naught, and z is 1, so going from e to the minus r over a naught to squaring that is e to the minus 2r over a naught dr. And some more simplifications we can make. The integral of phi here from 0 to 2 pi, integral d phi is just going to be 2 pi. And the integral of sine theta d theta from 0 to pi is going to be 2. That gives you a minus cosine, and minus cosine of pi minus cosine of 0 gives you, sorry, this didn't give you pi, it gives you 2. Gives me 2. Okay, so we have those values. So moving on to the next line, we're going to have a 4 pi on top here from these two, and the 4 pi will cancel with the pi to give us 4. So we have 4 over a naught cubed. And then once again our integral from minus infinity to infinity of r cubed e to the minus 2r over a naught dr. So now we need to figure out how to solve this integral that I've got in this r integral here. And I can look up in a table that the integral from 0 to infinity of x to the n e to the minus a x dx is just equal to n factorial over a to the n plus 1. Okay, so what is my n in this case? My n is 3. I can see that corresponds to this part. My x is just r. And my a is going to be 2 over a naught. So x equals r. We have n equals 3. And a equals 2 over the bore radius, 2 over a naught. Okay, we'll substitute that in now. We have the expectation of r for the 1s orbital. It's going to be 4 over a naught cubed of 3 factorial is going to be 6, 3 times 2 times 1, divided by, I'm going to do this second part separately. Since it's 2 over a naught and it's on the denominator here, I'm going to make this a naught over 2. So instead of being on the denominator, it's on the top now since I reversed that. And then this is to the 4th. Okay, so that gives us 4 times 6. 2 to the 4th is 16. And then we have an a naught to the 4th over a naught cubed. So we can see that this a naught cubed cancels, and with the 4th, leaving just one a naught left over. So our final answer for the expectation value of the radius is going to be 24 over 16 is 3/2 times a naught. Okay, so that's an example of how we calculate expectation values in spherical polar coordinates using the radius here. So that's the expectation value of the radius. There's another concept called the most probable radius, and this would be the radius at which there is the maximum amount of electron density. So if you were to pick a single radius which had the maximum probability of an electron occurring being measured at that radius, this would be that radius. So if I draw a plot here, let's say this function reaches a maximum, then goes down. So my most probable radius is this value right here, where I have in green this P of R, or the probability density, or the radial distribution function, probability density versus radius for some given function here. And this would be what the probability density or the radial distribution function would be for the 1s orbital. This is what it would look like. So this probability density function, which we call also a radial distribution function, we can say that this P of R that's going to be equal to, we can do this in a few different ways. One of them would be doing r squared times r star n of l of r, r n l of r, times the radial part of the wave function times r squared. And that's because of the volume elements here. As you get to larger and larger values of r, there's more and more volume that you're encompassing. So you need to take the regular probability density, the psi star psi, and then multiply that times r squared, gets us the radial distribution function here. So instead of just the decaying exponential, which we would have in our wave function, this decaying exponential here, multiplying it times r squared gives us this kind of peaked function here. And you could equivalently calculate that from integrating out the theta and phi dependence of your probability density. So integral from 0 to pi d phi of r squared psi star NLM psi NLM. So because it's going to end up depending on the quantum numbers n and l, it might be appropriate to call this probability density P of NL. If I can jam those in there. Okay, so what's this going to be for our case here of the 1s orbital? Well, we can see when we integrate out the theta and phi dependence, we just get 2 and 2 pi, since the theta and phi dependence is just 1. It doesn't vary with angle. It's spherically symmetric. What we're going to be left with is our probability density function is going to be, when we substitute that all out, we're going to have the 4 pi here divided by this gets squared, so it becomes a pi. Z, again, we're setting to 1, squaring, getting 1 over a naught cubed. Then we have e to the minus, z being 1, e to the minus r over a naught squared. So e to the minus 2r over a naught. And this multiplied times r squared. So settling this all out, again, canceling the pi's there, our final probability density function is going to be 4 over a naught cubed r squared e to the minus 2r over a naught. And that's this function here. It's a quadratic polynomial times a decaying exponential, and that gives you this increase at short range, decrease at long range, and a maximum somewhere in the middle. So we want to find out what this maximum, what this most probable radius is here, where we have the maximum amount of density, or the most likely radius to be measured. So we can do that by saying that the derivative of this function with respect to radius equals 0. We see the derivative of p with respect to r is 0 at this peak here. And that's going to happen when we have derivative with respect to r of the function 4 over a naught cubed, r squared e to the minus 2r over a naught. And this function is going to differentiate in the following way. We can factor out this constant here, 4 over a naught cubed. And we're going to have the product rule here. First one is going to be 2r e to the minus 2r over a naught. Differentiate r squared. Don't touch e to the minus 2r over a naught. And then the second term, differentiate this and don't touch this. We're going to get a minus. From the chain rule, we're going to get a 2 over a naught in there. R squared e to the minus 2r over a naught. And then reminder that this equals 0. So next step, we can factor this to get all of the various terms for the possibilities of what r values can equal 0. Well, we can factor out a 2 here, so we can get 8 over a naught cubed. We can also factor out an r from both terms. And we have, we can also factor out a 2 minus r, which remains, or sorry, it's not a 2 minus r. It's going to be a 1 minus r over a naught times e to the minus 2r a naught equals 0. And again, that's just algebraic factoring of this equation up here. So this leaves us with several possible values for what r's we can choose. We have r equals, either if this is 0, that would set the rest of it equal to 0, so r could be 0. In here, if we set r equal to a naught, this becomes 1 minus 1, so it could be the Bohr radius, a naught. And this e term here, if we set r equal to infinity, this will be equal to 0 as well, because e to the minus infinity will be 0. So 0, a naught, and infinity. And indeed, you do see that the derivative is 0 at r equals 0, but that is a minimum. That's not a maximum. And it's equal to 0 again at r equals infinity, but that's once again a maximum. So both of those are cases that we are not interested in. But this one here in the middle, that indeed is a maximum. And the value of r there is a naught. So our most probable radius is going to be r equals a naught, the Bohr radius. So Bohr was actually onto something when he was assuming those kind of fixed quantized orbits in the early Bohr model that we talked about, but not exactly in the way that he thought. So it's not that the electron was some particle orbiting at this fixed value of the Bohr radius for its total radius, but that it ends up that when you calculate it for the lowest energy state, this 1s orbital, the most probable radius is the Bohr radius. And then, interestingly enough, when we look at our expectation value for r, it's actually not that value, but it's at 3/2 of the Bohr radius. So this is generally going to be the case where you have the expectation value and the most probable radius are going to be different values. So we have the expectation value and most probable radius, and in general those are not going to be the same. And additionally, you could also think about integrating your wave function from a certain value to a certain value. So you could think about the integral from 0 to some big R of our radial wave function r star nl, rnl, r squared dr, and setting that equal to some value p, like p is a 90% of the electron density being inside of it, or some other value. But you see, there are different ways that we calculate this radius. We end up getting different values. So the concept of kind of the volume of an atom or a radius of an atom, it's quite muddy because of this way that the electron density is this probability here. So any choice for what the radius of an atom is going to be a somewhat arbitrary choice, and we just need to define well the terms we're using when we're referring to the radius of an atom, because as we can see, calculating different values for what the radius of the atom would be would give us different values. So that's something we need to keep in mind when you think about things like hearing it reported what the radius of a certain atom is, or things like that. That there's a lot of caveats, and it's pretty unambiguous and not well defined what the actual radius of an atom can be.